So I'll just spend a couple of minutes on revising what we had learned yesterday. So this is just a brief of the relationship between the normal t distribution, chi-square, and f distributed random variables. So yesterday we had talked about this, that a chi-square distributed random variable is nothing but sum of squared values of independently distributed standard normal variate. मीनिंग व्हाट, अगर आपके पास एक डिस्ट्रीब्यूशन है जो कि स्टैंडर्ड नॉर्मल वेरिएट है, मीनिंग विच दैट इज द डिस्ट्रीब्यूशन हैज अ मीन ऑफ 0 and variance of 1, and they are called as standard because all these variables are transformed into standard form. And by standard form, what we mean is we take all the raw observations, subtract the mean from all these raw observations, and divide the observation by its standard deviation. So the transformed variable, they are called as standardized variable. So if you have a distribution which is characterized by 0 mean and variance of 1, they are called as standard normal variable. So if you take n such independent normal variables, you square them up and you sum them, the resultant distribution that this statistic follows is your chi-square distribution. And as an example, all your sum of squares like variance, explained sum of squares, residual sum of squares that we study in econometrics, all these statistics follow a chi-square distribution. और chi-square distribution है तो उसके दो parameters होंगे, that is mean and variance. I am not talking about skewness and kurtosis for the time being, but I'm sure that you are aware that skewness and kurtosis are also related to the distribution in the form of third and fourth moments. So mean of a chi-square distributed random variable is equal to the degree of freedom, and variance of a chi-square distributed random variable is twice of that degrees of freedom. So these are certain characteristics of a chi-square distributed random variable. Second is about t distributed random variable. So that's where we learned that t distribution is a ratio of two independently distributed standard normal variable and a chi-square variable. So let us take a simple example, saying that z is a variable which comes out of a standard normal population, and y is a variable which follows a chi-square distribution with n degrees of freedom. So t statistic is defined as a ratio of a standard normal variable and a square root of the chi-square distributed variable with the degree of freedom given by this denominator. So this is a t distribution with n degrees of freedom. Third, this was a relation where we understood what f distribution is actually. So f distributed random variable is defined as a ratio of two independently chi-square variable, two independently distributed chi-square variable with their respective degrees of freedom. So there's a variable y1 which follows a chi-square distributed random variable with a degree of freedom n1, and there's this variable y2 which follows a chi-square distributed random variable with degree of freedom n2. So f ratio is defined as ratio of two independently distributed chi-square variable with their degrees of freedom. So f will be y1 upon n1. और एक और चीज हमेशा याद रखिएगा, which I have repeated time and again, that variation and variance are differed by, or they are distinguished by, the degrees of freedom. So when you divide a variation is nothing but squared values of the deviation y1 has a degree of freedom n1 and y2 has a degree of freedom n2. That's why f ratio is a distribution which is characterized by the degrees of freedom of numerator and denominator. And then one simple result which follows from this, that if you have a t distribution of n degrees of freedom, you square that distribution, you get a f distributed variable with 1 degree of freedom in numerator and n degrees of freedom in denominator. So these are some of the important relationships that exist between these distributions of normal, t, chi-square, and f distribution. Now we'll utilize some of these relationships as we go and discuss the hypothesis testing. I'll again repeat what we have done till now. So अभी तक हमने क्या देखा था, that जितने भी linear hypothesis हैं about the population coefficients or beta coefficients, all such examples of linear hypothesis can be generally fit into a linear framework, and that linear framework was written as R beta is equal to R. So where this R and small r is a matrix of known constant and small r is a vector of known constant, and this beta is your population parameters. But since हमारे पास ये beta नहीं होता है, since we do not know about the population parameters, but we want to test hypothesis related to the population parameters, so we replace this beta by what we call as OLS estimator, and they are denoted by B. So in order to test this hypothesis, that is null hypothesis, that R beta is equal to R, and all the examples that we have understood, whether the test of significance hypothesis or sum of the two coefficients equal to a particular value, or two coefficients being equal, or the test of overall significance of relation, all such examples can be fit into this general linear framework. And since we do not know about this population coefficient, we replace this by OLS estimator. And then we define a statistic which we write as RB minus R. So now, in order to draw any inference about the population parameters, I must have a sampling distribution. Sorry. I must know the sampling distribution of this statistic, that is your RB minus R. Because इसका जो sampling distribution आएगा, इसी के basis पे I'll be able to draw the inference about the hypothesis that we have regarding the population coefficients. And that's why we need the sampling distribution of the statistic, which is your RB, and B here is OLS estimator minus R. And this is a vector which gives you the difference between the expected value and the observed value. Now, in order to define, or in order to determine the sampling distribution of this statistic RB minus R, that's how we proceeded in our previous lectures. So let us focus here. So we know that OLS estimators are the linear and unbiased estimator. So unbiasedness का मतलब क्या है कि अगर मैं average करूं इस OLS estimator को, that is if I take expectation of OLS estimator, it must be equal to the true population coefficients. So अगर expected value B beta है, तो expected value of R times B, where R is a matrix of known constant, it will also be R times beta. So RB has a mean which is your R beta, and the other parameter that I require in order to draw inferences is your variance of RB. So variance of RB हमने calculate किया था, and that came out to be R sigma square X transpose X का inverse multiplied by R transpose. So RB, and yesterday I also told you that how we are able to write that RB is normally distributed, because since B is a linear function of error term, where error term is supposed to be normally distributed. So the property of a normally distributed random variable is that any linear combination of a normally distributed random variable will also be normally distributed. So in a similar
Sir, we lost your audio, sir.
are you able to hear me now?
Now we can hear you.
Oh, I'm really sorry. Actually, there's some internet issue in my state, and the place where I live, there is no Wi-Fi. So That's why some such issues are there. So just bear with me. जहाँ भी आपको disturbance लगे, please interrupt me there only. अब
सर
voice clear आ रहा है? हाँ जी.
वो डिफरेंस वाले पार्ट भी लॉस्ट यू जहाँ पे आप वेरिएंस एंड वेरिएशन का डिफरेंस बता रहे थे.
Okay. So I'll just repeat that point. Uh, ये देखो एक सिंपल एग्जांपल लेते हैं कि मान लो मेरे पास एक सम एक ऑब्जर्वेशन से एक्स आई आई डिनोटेड बाय एक्स आई. सो मान लो x1 x2 x3 करके मेरे पास सारे n नंबर ऑफ वेरिएबल्स हैं, n नंबर ऑफ ऑब्जर्वेशंस हैं. सो फर्स्ट थिंग दैट वी डू इज वी कैलकुलेट इट्स मीन. I do it x bar. That's how we calculate mean. That is, you sum all the numbers and divide it by the number of observations. And then, in order to calculate variance, you see how the formula goes. You take each of the observations, you subtract each of these observations from the representative value, that is a mean value. Then you square them, and then you simply take a sum. So when you only calculate this part, this is your variation. That is sum of squares of the deviation form values or sum of squared values of deviation forms. Now, if I'm talking about calculation of variance, the correct formula should be ideally n minus 1. If you follow, because in order to calculate variance, first मुझे mean निकालना चाहिए. Because without mean, I'll not be able to talk about variance. But if you have n number of observations and if you have calculated mean out of using all those n observations, so you have fixed one particular observation. And now, in order to calculate any new statistic, you are only left with n minus 1 free observations. So ideally, if you read very carefully in statistics textbook, ideally the formula of variance, as far as sample variance is concerned, it should be n minus 1. What is this n minus 1? This n minus 1 is your degree of freedom. So if I do not divide this expression by n minus 1, this is just variation. And if I divide this variation by degrees of freedom, this becomes variance. Similarly, जो आपका total sum of squares, explained sum of squares, residual sum of squares, they all are examples of variation. When you divide them by degrees of freedom, they'll become variance. And that's why when you divide RSS by degree of freedom, that is, I'm sure that हमने ये चीज पढ़ा था that, an unbiased estimator of sigma square is E transpose E upon n minus k, where E transpose is nothing but your residual sum of squares. So residual sum of squares per se is a variation, but when you divide that residual sum of squares by its degree of freedom, it becomes variance. And this, in this particular case, is an example of an unbiased estimator of the population variance. So ये difference है variance और variation में, ये याद रखिएगा. Is this clear?
Yes, sir.
Yes, sir.
Is this clear? Okay, shall I move ahead?
Yes, sir.
Okay, all right. Okay. So I was still here. That is, we defined that B, RB भी normally distributed होगा क्योंकि B is a linear combination of the error population, and error population is assumed to be normally distributed with mean zero and constant variance, which is what you call as homoscedastic error variance. So RB भी मेरा normally distributed होगा with mean R beta and variance given by this term. And so this is my raw observation. If I take each of these raw observations, subtract mean from this, so RB minus
So we lost your audio again. Sorry, sir.
Is this clear now?
For you clearly.
अभी ठीक है?
Hasa, it's better, but actually after 10 minutes, we are losing you for a few seconds in between.
Just give me a second. I'll reconnect and come back. Just give me a second. Guys, can you hear me now?
Yes, sir.
Yes, sir.
Okay, I just hope it continues. Okay, all right. So if I subtract all these raw observations around its mean value, so जो मेरा deviation form में observation होगा वो mean होगा उसका 0, no, because all of these are subtracted from r beta. So जो mean होगा deviation form का, that is summation xi minus x bar, अगर आप ऐसा करो तो ये 0 होगा. Same thing I have utilized over there. So now RB minus beta will be normally distributed with mean 0 and variance given by this term, because variance will be unaffected by change of origin. Now again I told you in the last class कि जितने भी हम टेस्ट करते हैं, जितना भी hypothesis testing होता है, वो assumption मान के ही होता है कि आपका null hypothesis true है. ठीक है? So in this case also assuming null hypothesis to be true, which is in this case R beta is equal to R, which is my actual null hypothesis about the population. So assuming null hypothesis to be true, I can replace this R beta by R. So here I have got the sampling distribution of the statistic which I actually need for this vector RB minus R, because ultimately I need to, I want to draw inferences about my population parameter beta from this statistic which is given by RB minus R. So your RB minus R as a statistic is normally distributed with mean 0 and variance given by this term. Is this clear till here? All of you? Is this clear till here? I've just repeated what we have done so far.
Yes, sir.
Yes, sir.
Shall I move ahead?
Yes, sir.
Okay. अब इस point को याद रखिएगा कि ये जो मेरा statistic है RB minus R, it comes from a population which is normally distributed with mean 0, but variance is not identity matrix. That is, it is not coming from a standard normal variate. But it is called IIDs. All of you? Are you guys aware what is IIDs?
No, sir.
No.
Hello. Am I audible?
Anyone? Neil, what is an IID?
Sir, I know the I stands for independent.
Okay.
Uske baad, I do not know, sir. I think independent distribution, but I don't know what the other I should be.
Independent identical distribution.
Yeah.
Since each
Yeah.
element in that distribution would have same probability function.
Correct. Correct. I'm sure that you are aware of something called central limit theorem,
Yes, sir.
right?
Yes, sir.
So central limit theorem जो होता है वो IIDs से ही आता है. IID क्या है? IID stands for independent and identically distributed, variables. Meaning what? That अगर कोई variable IID है, it means it comes from the same population, so it will have the same population or probability density function, and they all are independent as well. And yesterday we had talked about what exactly we mean by statistically independent variables, meaning which that if you talk about the joint probability or joint occurrence of such independent variables, you can simply multiply their marginal probabilities. This is what statistical independence means. So when you hear a term IID, you must understand that all the observations have come from the same population, and that's why they follow the same probability density function in case of a continuous function, and they all are independently distributed. That is, probability of selection of one in such type of distribution does not affect the occurrence of probability of selection of the other variables. And central limit theorem is based on this fundamental, property of distribution. And so RB minus R here is a normally distributed random variable. So it comes from a distribution. It comes from a family of distribution which is normally distributed, And normally distributed अगर है तो इसका mean और variance क्या है? It is normally distributed around the mean 0, and the variance of this variable or this statistic is given as R sigma square X transpose X inverse R transpose. ये बात यहां तक इसको याद रखिएगा, because I'll be using this important result later on. Okay, now proceeding ahead, I'll require some of the important results that we'll use. So that's where test hypothesis statistic will be derived. And again, I'm telling you, I'll not ask these derivations at all anywhere. All these derivations are done purposefully so that you understand the mechanism behind such test rather than just following what is actually given in the textbook. Okay. So let us understand this result. It's a very important result that we'll use in this hypothesis testing. So what it says that suppose there is this vector of variables x, and let's say there are k number of variables in this, and this x is normally distributed with mean 0 and variance given by identity matrix. So this is a standard normal variable. So x consists of k number of such variables. All these k number of variables comes from a family of standard normal distribution, meaning which that all these k variables have mean 0 and variance of unit, or they have unit variance. So I'm sure that by the relation of the z variable and chi-square, you can simply think that if I take all these k number of variables, I square them and I sum them up, the resultant statistic that it will follow will be a chi-square distributed variable. So matrix के notation में कैसे लिखते हैं sum of squares? I take the vector and I pre-multiply that vector by its transpose. So x transpose will be nothing but summation xi square. And how many variables are there? K number of such variables are there. So x transpose x will be a chi-square distributed random variable with degree of freedom given by this k, assuming that there are k variables in this vector x. Now, again, same x, and suppose this is still normally distributed, it still has a mean 0, but now the variance is given by this constant sigma square identity. That is, it has a constant variance, but now the variance is not 1. तो अब मुझे इसको स्टैंडर्ड नॉर्मल वेरिएट बनाने के लिए हर एक ऑब्जर्वेशन को इसके स्टैंडर्ड डिवीजन से डिवाइड करना पड़ेगा, क्योंकि मीन तो एनीवे 0 है, बिकॉज आई नो दैट z क्या होता है xi माइनस x बार अपॉन स्टैंडर्ड डिवीजन ऑफ x. Sorry, x bar is already 0 because it comes from a normally distributed population having mean 0. So in order to convert this x, which is now no longer a standard normal variable, I have to divide each of these raw observations by its standard deviation. And then if you square them and sum them up, it will again be a chi-square distributed random variable with the degree of freedom given by k. So it will be x1 square upon sigma square plus x2 square upon sigma square, so on till xk square upon sigma square. Why sigma square? Because each of them has the same equal variance. So if you take sigma square 1 upon sigma square common, again it will be 1 upon sigma square x transpose x will be a chi-square distributed random variable, and this can also be written as x transpose sigma square inverse x is a chi-square distributed random variable with degree of freedom given by k. Now, you can draw a simple analogy for this standard normal variable. Yeah.
In this part.
Come again?
So this part where we are writing it as, why we are writing it as inverse of the variance? Like why we are taking this variance in the inverse form?
Because
okay,
यहाँ पे
okay,
तो
got it,
denominator में ना dear, है ना?
Yeah, got it.
Yeah. Okay. So again, if you draw this, so now इस x को आप rb minus r से replace करो. So rb minus r is a statistic which is normally distributed with mean 0 and variance given by this. So I can write this RB minus R exactly into this form, and the resultant statistic that I'll generate will be a chi-square distributed random variable. Now, if you are aware that RB minus R will have a dimension Q, because R has a dimension Q times K, B is your K times 1. So जो resultant matrix आएगा या जो subtraction of matrix होगा उसका dimension भी Q होगा. So I'll have Q number of such variables. So RB minus R is normally distributed with mean 0 and variance given by this. I'll express this RB minus R into its sum of squares form, and I can write that as X transpose. So X square replaced by RB minus R. So RB minus R ka transpose. Variance ka inverse. So this is the variance, uska inverse multiplied by RB minus R. This whole statistic will be a chi-square distributed random variable with degrees of freedom given by Q. Why Q? Because there are Q number of such variables here in this statistic RB minus R. So again, follow this result. We'll use this when we move ahead. Is this clear till here, all of you?
Yes, sir.
Sir.
Agar nahi, I'll repeat this again, but just
Sir.
tell me honestly. हाँ जी.
Sir, can you scroll up?
हाँ जी.
Sir,
So X transpose X. That the this X has changed from X variance has changed to sigma square into I.
Because यहाँ पे मैंने अब X को इससे define किया ना dear. Now X comes from a normally distributed random variable, but it now has a variance which is given by a homoscedastic variance, which is sigma square I.
So you're defining that on your own.
Yeah, that's what I've written. Now, if X is this,
You got it, sir.
ये सिंपली समझाने के लिए था कि अगर x मेरा ऐसे रिटर्न है तो जो सम ऑफ स्क्वायर्स होगा वो एक chi स्क्वायर डिस्ट्रीब्यूटेड रैंडम वेरिएबल होगा. बट सिंस सबका यहाँ पे स्टैंडर्ड डेविएशन एक है, इसलिए यू डू नॉट डिवाइड इट बाय इट्स वेरिएंस इन ऑर्डर टू कन्वर्ट इट टू स्टैंडर्ड नॉर्मल वेरिएबल, बिकॉज इट इज ऑलरेडी कन्वर्टेड इनटू दैट. But if I have a normally distributed random variable, first I convert into standard normal variable. How do I convert into standard normal variable? I divide each of those observations by its respective standard deviation. Standard deviation यहाँ पे मेरा क्या है? Sigma. और then I square all of them and then sum them up. So that's why x1 upon, तो ये क्या है मेरा ideally? x1 upon sigma, x2 upon sigma से लेके xk upon sigma. Then how do I obtain chi square? I square all of them and then sum them up. Is this clear?
Yes, sir.
Sir, I again have doubt on the when you write it at as inverse of sigma square inverse when you write it. So this part is basically matrix multiplication, right? X.
Yeah.
So if you're taking it like not be outside, because if you're keeping it in the middle, so does it affect distribution? Does it follow the same distribution? That's what I'm not understanding, because that's
first of all, understand this part. Extra span
so
x trans x क्या है आपका dear? अगर मान लीजिए x आपके पास let's say k number of variables आपका, जो x transpose x आएगा वो आपका scalar quantity आएगा. It is all multiplied by ये r आपका एक matrix of known constant है. Sigma square is a scalar.
Is it a single value? You're saying it's a single value that we'll get for this x transpose
Correct.
x. Sir, I missed out on few classes, so that's why I'm confused.
No issue. कोई बात
Okay.
नहीं.
I'll go and read.
Yeah. Is this clear? Shall I move ahead or should I explain it once more? How do I come from here till here? Shall I explain it once more or should I move ahead?
Sir, understood.
Okay, all right.
So one
So,
little doubt.
हाँ बोलिए.
जैसे x is the vector of k variables, वैसे rb minus r is a vector of q variables, right?
Correct. It is a dimension q, dear. याद करो R को हमने कैसे डिफाइन किया था? It's a matrix of known constant of q by k, right? तो B से मल्टीप्लाई करने के लिए B का डायमेंशन k by 1 होगा, क्योंकि it's a कोएफिशिएंट वेक्टर. सो जो रिजल्टेंट मैट्रिक्स होगा वो क्या होगा? q by 1. अब इसको मैं सब्ट्रैक्ट किससे कर रहा हूं? R से. तो ये सब्ट्रैक्शन तभी पॉसिबल है जब दोनों का डायमेंशन सेम हो.
Yes.
है ना? Addition of vectors will not be possible if they are of different dimensions.
And so here in place of x, we are substituting rb minus r just because x follows a normal distribution and even rb minus r follows a normal distribution.
Correct. ये सिंपल, ये इतना पार्ट जो था ये एक्सप्लेन करने के लिए था कि यहां से मैं यहां पे कैसे लिख रहा हूं. That's it.
Okay, got it, sir.
है ना? सो अगर आप एक्चुअली फॉलो करो तो ये पार्ट क्या है? एक मेरा x है जो एक वेरिएबल है जो कि नॉर्मली डिस्ट्रीब्यूटेड था. जब मैं इसको सम ऑफ स्क्वायर, इसके सम ऑफ स्क्वायर्स में जब ट्रांसफॉर्म कर रहा हूं तो ये काई स्क्वायर डिस्ट्रीब्यूटेड वेरिएबल बन जाता है. और वो काई स्क्वायर डिस्ट्रीब्यूटेड वेरिएबल को अगर वेरिएंस यूनिटी नहीं है तो क्या होता है? वो वेरिएंस इनवर्स उसके बीच में आके और वो काई स्क्वायर वेरिएबल ऐसे लिखा जाता है. दैट्स इट. So my RB minus R is a statistic which is a normally distributed random variable with mean 0 and variance this. If I have to write this in the sum of squares form, so what I do, I take its variance, I invert it, and then I pre-multiply and post-multiply the transpose of the vector. That's it. Chalega?
So just एक और चीज, even if we don't have the variance as a transpose in the middle, it will still be a chi-square vector, right?
It will still be a chi-square vector. Yeah. ये वेरिएंस क्यों आता है नील? क्योंकि इसका वेरिएंस यूनिटी नहीं है. समझ में आई बात? जैसे देखो, जब स्टैंडर्ड नॉर्मल वेरिएबल को हमने किया था तो यहाँ पे वेरिएंस का फैक्टर नहीं आ रहा क्योंकि सबका वेरिएंस 1 है.
Oh yes, sir. Because we have to ensure that if we want z score, if we square it up, तो obviously variance has to be.
सबको उसके वेरिएंस से डिवाइड, स्टैंडर्ड डेविएशन से डिवाइड करना होगा तुम्हें, तभी वो z में कन्वर्ट होगा, राइट?
Yes, sir. Got it, sir.
है ना? Okay. Shall I move ahead? Shall I move ahead, guys?
Yes, sir.
Yes,
Okay, all right. Now, I use a general result and I'll not prove this. I'll just use this result, which is this part. And why do I need this? I'll tell you, once we derive that statistic. So, एक result क्या है? ये result है आपका कि अगर एक variable है x, which is normally distributed with mean 0 and variance given by this, and if there is a symmetric matrix which is idempotent given as A of rank R, then 1 upon sigma square x transpose AX follows a chi-square distribution with degree of freedom given by the rank of this matrix A. Okay, this is the general result. What this result says is that if you have a normally distributed random variable, and if there is a matrix which is symmetric and idempotent of some rank, then 1 upon sigma square, which is the variance of the normally distributed random variable, x transpose that matrix A, x will follow a chi-square distributed random variable with degree of freedom given by the rank of the matrix. Now, where do I actually apply this result will matter more. So, this is my residual, sample residual. I can write this residual as y minus xb, और b को मैंने replace किया है solution से. So I've replaced b by x transpose x inverse x transpose y. Now if you take y as common, this will become I minus x transpose x inverse x transpose. You must understand this is scalar, but x transpose is not a scalar quantity. So ये जो part है I minus this vector, this is called as M, and this is also called as residual maker matrix. I'll tell you later on why this is called residual maker matrix, is because this is a matrix when it gets pre-multiplied by a vector of variable, it produces a vector of residuals of a regression of that variable on X. I'll repeat this again. This M is called your residual maker matrix. That's why you see here E is written as M times Y. So what is this matrix? What is this doing? I have a vector of variable defined as the dependent variable Y. And if I pre-multiply this vector of variable by M, which is the residual maker matrix, I get the vector of residuals of regression of Y on X. So by the same logic, if I have M times X, what it means? This residual maker matrix is doing what? It will give me, or it will produce a vector of residuals of regression of X on X itself. So M times X must be 0.
Sir,
I'll repeat this point. This portion, M is your I minus X, X transpose, X inverse, X transpose. This I write for shorthand as M, and this M is called your residual maker matrix. नाम क्या है इसका? Residual maker. How do I define it? This matrix is defined as that when this matrix gets pre-multiplied by a vector of variables, it produces a residual vector of regression of Y on X, or of dependent variable on independent variable. ऐसे आप इसको समझो. So if I tell you that M is multiplied by X, where X is nothing but your dependent variable and independent variable both. So इसका मतलब क्या है? That it will, this product will give me a residual vector which will be a regression of X on X itself. That is independent variable का और dependent variable दोनों same है. In this case, residual vector will be 0. So M times X will be 0. Now, what is the property of this residual maker matrix? I told you, if you remember from our earlier lectures, that जितने भी टाइप के हम मैट्रिक्स mostly use करते हैं econometrics में, first of all of them are square matrix, and after that they are also symmetric and idempotent matrix. So M also, that is residual maker matrix, also is a symmetric and idempotent matrix. So E can also be written as M times Y. And mind you guys, this is a very powerful result, because ये तुम्हें क्या बताता है? ये तुम्हें उतना regression करने की जरूरत ही नहीं है. If you have the data matrix, you calculate this area, this part, X transpose, X inverse, X transpose. You subtract this calculation by an identity matrix of order, और उसको जब आप अपने Y वैल्यू से मल्टीप्लाई करोगे, आपको रेसिडुअल वेक्टर आ जाएगा सीधे. Now, if I just write this E in the form of M times Y, I replace this Y by X beta plus U, which is the population regression function. So if you expand this, this will become Mx beta plus M times U. I already told you that Ymx should be equal to 0. So E can also be written as M times U. Now again, this is a very powerful result. So if suppose you have the vector of errors of the population, which is very unlikely. So if you have the vectors of errors of the population, if you pre-multiply that vector by the residual maker matrix, you'll get the vector of residuals. और इसलिए भी पावरफुल है ये कि अगर मैं दोनों साइड ऑफ एक्सप्रेशन में m inverse से multiply करता हूं, so if I have the vector containing residuals and if I obtain m inverse, so m inverse E will give me U, which is my population error. That is, you can go from sample residuals to actual errors of population via this residual maker matrix. That's why these are some very powerful results which are not mentioned in many textbooks. So E can also be written in the form of population error, which is m times U. अब मुझे residual sum of squares लिखना है, तो I can easily pre-multiply this E by E transpose. So E transpose E can be written as U transpose M, M transpose U. Sorry, U transpose M transpose times MU. And since M is an idempotent matrix, M transpose M can be simply written as MU. So what I have got here is that E transpose E can be written as U transpose MU. ये M कैसा मैट्रिक्स है? M है सिमेट्रिक मैट्रिक्स एंड आइडेम्पोटेंट मैट्रिक्स. Now, errors, population errors are assumed to be normally distributed with mean 0 and variance, that is homoscedastic variance. I can write this, that is, I can utilize this result, which I have written here. That is, I can write this as 1 upon sigma square mu transpose mu will follow a chi-square distribution with degree of freedom given by the rank of this matrix M. And I can replace this mu transpose mu by E transpose E, because mu transpose mu is also your E transpose E. So now E transpose E upon sigma square, which sigma square is the error variance of the population error variance. So residual sum of squares divided by population error variance follows a chi-square distributed random variable with rank or degree of freedom given by rank of the matrix M. अब ये M क्या है मेरा? M है I minus this term. That is identity matrix of order n, and this is my x multiplied by x transpose x inverse x transpose. अब ये एक property है, and before that property, let me tell you what trace of a matrix is. Trace of a matrix is nothing but sum of all the diagonal elements of the matrix.
Sir, एक चीज can you just scroll up for just 10 seconds?
Yeah.
So,
हाँ जी.
so I didn't get this part. Why mx is equal to 0?
M क्या है dear आपका? M is residual maker matrix which transform a vector of variable or which produces a vector of residuals of a regression of y on x. So that's why M times y gives you E. So M times x क्या होगा? It will give me a vector of residuals of a regression of x on x itself. Do we understand this?
Basically, covariance of जो dependent variable and error term is basically 0. So that's why mx is equal to 0, if I'm not wrong, right?
That is also there, but this M here is the residual maker matrix. तो आपका अगर आप x को x पे regress करोगे, तो obviously there will be no errors, no residuals.
Okay, got it, sir.
So नहीं बात, यहाँ मैं y को x पे regress कर रहा हूँ, इसलिए जब मैं इसको pre multiply करता हूँ m से, तो मुझे vector of residuals मिलता है. But जब मैं x को x पे regress करूंगा, तो obviously the vector of residuals will be a zero vector.
Sir, could you repeat from the E transpose E वाले part के बाद से?
Yeah, I'll do that. So E जो है आपका, that is vector of residuals, can be written as M times U. U आपका population error है, ठीक है? अब जब मैं E ट्रांसपोज E करूंगा, E ट्रांसपोज E क्या है मेरा? रेसिडुअल सम ऑफ स्क्वायर्स. So E transpose E means what? MU का transpose. So AB का transpose will be B transpose A transpose. So it will be U transpose M times U. अब ये M जो है रेसिडुअल मेकर मैट्रिक्स इज अ सिमेट्रिक एंड आइडेम्पोटेंट मैट्रिक्स. आइडेम्पोटेंट का क्या प्रॉपर्टी है? इफ यू कीप ऑन मल्टीप्लाइंग द मैट्रिक्स बाय इटसेल्फ, द रिजल्टेंट मैट्रिक्स इज द मैट्रिक्स इटसेल्फ. So M transpose M will give you M only. So this can be written as U transpose MU. ठीक है?
सर उसके बाद वाले पार्ट से.
हाँ, उसके बाद मैंने क्या किया? अब जो ये एरर पॉपुलेशन है मेरा, एरर जो है इट इज अज्यूम टू बी नॉर्मली डिस्ट्रीब्यूटेड एंड मीन जीरो एंड कांस्टेंट वेरिएंस. करेक्ट?
यस सर.
ठीक है. अभी हमने ऊपर क्या एक जनरल रिजल्ट देखा है. जो मेरा जनरल रिजल्ट है वो ये है कि अगर मेरा कोई वेरिएबल है which is normally distributed with mean zero and a homoscedastic variance, and if there is a matrix which is symmetric and idempotent, I can express this by saying that 1 upon sigma square, which is the variance of this x transpose that matrix A, follows a chi-square distributed random variable with the degree of freedom given by the rank of this matrix. Correct?
Yes sir, got it.
ठीक है. सो
Yes,
अब इसी रिजल्ट को मैंने सिंपल यहाँ पे लिखा है कि सिर्फ जो मेरा एरर है वो भी नॉर्मली डिस्ट्रीब्यूटेड विद मीन जीरो एंड होमोस्केडास्टिक वेरिएंस. आई कैन राइट दिस एज 1 upon sigma square U transpose MU follows a chi-square distributed random variable with degree of freedom given by rank of this matrix. ठीक है.
yes sir.
And I have replaced this U transpose MU by E transpose E.
Yes sir, आ गया सर.
चलेगा?
Yes sir, got it.
So ये जो statistic है मेरा E transpose E upon sigma square is a statistic which follows a chi-square distribution, and the degree of freedom of this statistic is given by the rank of the matrix, which is the symmetric and idempotent matrix. ठीक है. Now, in order to calculate rank of a matrix, again I'm telling you, I'll not ask the derivation. I'm just explaining all this so that you understand the mechanism behind it. Rank of a symmetric and idempotent matrix is easily calculated by calculating its trace. अब trace क्या होता है? Trace of a matrix is nothing but sum of all the diagonal elements of the matrix. जितने भी एलिमेंट्स इस डायगोनल प्रिंसिपल डायगोनल पे होते हैं उन सब का जब आप सम करोगे, वो जो सम होता है उसको ट्रेस ऑफ अ मैट्रिक्स बोलते हैं. सो इफ आई हैव टू टॉक अबाउट रैंक ऑफ अ सिमेट्रिक एंड अदरवाइज रैंक निकालना मैट्रिक्स मेथड से बहुत ही टीडियस हो जाता है. यू कीप ऑन डूइंग द वेरियस इन्वर्जन बाय पहले आप किसी भी एक रो को जीरो करना चाहते हो, देन दैट्स हाउ यू कैलकुलेट द रैंक. सो एक बहुत ही ब्यूटीफुल प्रॉपर्टी है सिमेट्रिक एंड आइडेम्पोटेंट मैट्रिक्स का कि if you have to calculate rank of such matrix which is symmetric and idempotent, you can easily calculate rank of a matrix by calculating its trace. ठीक है. अब क्या है? सो ये मेरा M क्या है? M is identity minus this. Identity here is N. That is the identity matrix is of dimension N. And अगर आप इसको आप ब्रेक करोगे, so इसका जो dimension आता है वो आता है K. That is, it will be the trace of this matrix will be K. So trace of identity minus trace of this portion. Identity because 1 1 1 सारे diagonal element पे आप सबको sum करोगे, it will be N. For the time being, just understand that trace of this particular portion is K. So trace of M is N minus K, which is also rank of the matrix M. So this statistic E transpose E upon sigma square is a chi-square distributed variable with the degree of freedom given by n minus k. Just for the time being, just understand this part. That I have a statistic, and that statistic is the residual sum of squares divided by error variance follows a chi-square distributed random variable given by degree of freedom given by n minus k. ठीक है, इसको हम सिंपली ऐसे भी, तो जहां पे मेरा सिग्मा स्क्वायर है, सिग्मा, अब यहां से आप इजीली देख सकते हो जो एस स्क्वायर विच इज एन अनबायस्ड एस्टिमेटर ऑफ पॉपुलेशन वेरिएंस है, एरर वेरिएंस, that is also nothing but RSS upon n minus k. It is also a chi-square distributed random variable with degree of freedom given by n minus k. Now, so just for the time being, ye result, that is E transpose E upon sigma square follows a chi-square distributed random variable with degree of freedom n minus k, and the result that we had noted above, this portion, इन दोनों को हम कंबाइन करेंगे, and that's where we derive the statistic which will be used for various hypothesis tests. Now, जो मेरा इक्वेशन था RB minus R transpose.
Sir, एक second, can you just scroll up just?
Yeah.
Just थोड़ा सा. बस. Done, sir.
ठीक है, अब जो हमने निकाला था that X transpose variance inverse, वो मेरा ये क्वांटिटी है. For the time being, let me just not write this. ठीक है, this was the quantity that I had got, and this is a chi-square distributed random variable with degree of freedom given by Q. ठीक है, but एक problem है इसको अप्लाई करने में, and the problem is with this part, sigma square. ये sigma square, this sigma square is variance of the population error, which is mostly not known. So how do I overcome this part is where I utilize this portion. So I replace this sigma square, which is in inverse in numerator. So if I write in denominator, and I can replace that sigma square by E transpose E upon n minus k from here. So now my statistic can be written as RB minus R transpose R X transpose X का inverse R transpose का inverse RB minus R, और जो मेरा यहाँ सिग्मा स्क्वायर था वो इनवर्स में है तो डिनोमिनेटर में आ जाएगा, उस सिग्मा स्क्वायर को आई कैन रिप्लेस बाय दिस क्वांटिटी. Now you see this portion was a chi-square distributed random variable with Q degree of freedom. So I have got a ratio where in the numerator I have a chi-square distributed random variable, and the denominator I have a chi-square distributed random variable. Numerator has a degree of freedom Q, denominator has a degree of freedom n minus k, and they both are independently distributed. And this is the statistic. So let me call this as test statistic. And since this is a ratio of two independently distributed chi-square variable with degree of freedom given as Q and n minus k, so this also become your F statistic with degree of freedom as Q n minus k. And this is the final test statistic. अभी तुम्हें expression काफी बड़ा लग रहा होगा जब when we simplify this for all the examples that we have written so far. you will see the beauty behind this expression. So for the time being, understand that this is the this is a test statistic that you have in front of you. कैसा टेस्ट स्टैटिस्टिक है? इट इज अ एफ स्टैटिस्टिक. एफ क्या होता है? एफ डिस्ट्रीब्यूशन इज रेशियो ऑफ टू इंडिपेंडेंटली डिस्ट्रीब्यूटेड chi स्क्वायर वेरिएबल. न्यूमरेटर का डिग्री ऑफ फ्रीडम है q, डिनोमिनेटर का डिग्री ऑफ फ्रीडम है n minus k. So the test statistic that we obtain in order to conduct linear hypothesis about the population parameters is actually a F statistic. And here we'll try to differentiate that when we have simply one linear hypothesis, that is when we have simple linear hypothesis, in the case like test of significance or equality of coefficients or sum of two coefficients equal to a particular value, and when we have test of overall significance of relation. In the case of simple linear hypothesis, both these statistic, F statistic and T statistic, can be used interchangeably, because I know that F is nothing but square of a T distributed random variable. But when you have a compound hypothesis like test of overall significance of relation, where you have more than one simple hypothesis combined at a given point of time, that's where only F statistic can be used. And now you can relate your understanding or knowledge जो आपने अभी तक gather किया होगा, कि जब आप simple test of significance की बात करते हैं, that's where you use only T test. And you talk about T ratios. But when you talk about ANOVA testing or test of overall significance of relation, that's where you calculate this F ratio, which you write ESS upon RSS. And you can simply notice here that this portion is nothing but your RSS, obviously by degree of freedom. So denominator में आपका already RSS है. In the case of compound hypothesis, this numerator will turn out to be ESS, that is explained sum of squares divided by its own degrees of freedom. But जहां पे simple linear hypothesis की बात आएगी, वहां पे या तो आप F statistic use कीजिए या इसी का square कीजिए, वो आपका T statistic होगा. And let us now proceed one by one and just understand how this expression can be. Yeah.
So why we divided R minus B R वाला पूरा को divided by E transpose E n minus K?
Because यहाँ पे sigma square है ना dear, ये portion
So,
which is in
and
inverse.
how is sigma square equal to this part? I didn't get that.
Sigma square क्या है आपका? Population error variance, right?
Yes, sir.
Population error variance हमें नहीं पता होता है, तो इसको हम किससे estimate करते हैं? RSS upon n minus k.
Okay.
This is an unbiased estimate. एक तो ये logic है, और एक दूसरा जो हमने यहाँ पे result obtain किया था, this part E transpose E upon sigma square is a chi square distributed random variable with degree of freedom n minus k.
Okay, sir.
So E transpose E upon n minus k will also be a chi square distributed random variable, which can be substituted for unknown population error variance.
Okay.
Is that
got
clear?
it. Yes, sir.
Okay, all right. Now we'll proceed one by one and look how we can utilize this when we have various linear hypotheses that we have used. So let me just start with the first example. Let me write the statistic here first. So this is your statistic that we have got. अब देखते हैं, सबसे पहला मेरा क्या था हाइपोथेसिस। मेरा सबसे पहला हाइपोथेसिस है कि कोई भी एक जो पॉपुलेशन कोएफिशिएंट है वो 0 है, दैट इज bi is equal to 0. For the sake of simplicity, we'll take only 3 variables. That is, our population regression function is now, मेरा null hypothesis क्या है? One second. मेरा null hypothesis है, let's say bi is equal to, मेरा null hypothesis मान लीजिए b1 is equal to 0 है, ठीक है। अब मुझे इसको किस में फिट करना है? मुझे इसको इसमें देखना है, rb माइनस r में मैं कैसे फिट करूंगा। सो व्हाट इज दिस एक्चुअली में? दिस विल बिकम rb माइनस r। rb माइनस r मुझे क्या देगा? r इज ऑलरेडी 0। अब मुझे r कैसा लगेगा? मुझे r will look like 0 1 0, b will look like b0 b1 b2, right, minus of 0. So this is my rb minus r statistic. So rb क्या देगा मुझे? b0 multiplied by 0 will be 0, b1 multiplied by 1 will be 1, and b2 multiplied by 0 will be 0. So rb minus r से मुझे सिर्फ b1 आएगा। क्लियर है ये? Is this clear, guys?
सर एक्चुअली वो 0 1 0 जो लिखा है सर कॉलम वेक्टर, उसको
आवाज नहीं आ रही, could you please speak a bit louder?
सर जो रो वेक्टर आपने 0 1 0 लिखा है सर,
हाँ जी
सर उसको एक्सप्लेन कीजिए सर, वो कैसे होगा 0 1 सर?
ये कैसे आया?
यस सर।
क्या डेयर मेरा क्या है? बीटा 1 0 होना चाहिए, इसको मैं इस फॉर्म में फिट कर रहा हूं। सो मेरा बीटा बीटा क्या है? मेरा बीटा यही तो 3 कोएफिशिएंट है। सो लेट मी राइट बीटा माय लाइक दिस, ठीक है। अब ये क्या है? आर बीटा इज इक्वल टू आर शुड बी 0, तो यहां पे मेरा 0 होना चाहिए। तो ये जो मेरा मैट्रिक्स ऑफ नोन कांस्टेंट है विच इज योर आर, वो कैसा होना चाहिए? विच गिव्स मी द प्रोडक्ट ऑफ दीज टू टू बी 0. So मेरा null hypothesis that beta only beta 1 should be equal to 0. If my null hypothesis was that beta naught plus beta 1 plus beta 2 is equal to 0, in that case मुझे यहाँ पे सारा 1 1 1 चाहिए। तभी जब मैं इसको मल्टीप्लाई करूंगा, बीटा नॉट मल्टीप्लाइड बाय 1 प्लस बीटा 1 मल्टीप्लाइड बाय 1 प्लस बीटा 2 मल्टीप्लाइड बाय 1, they all will be equal to 0. But do I need that? I only need beta 1 equals 0 because that's what my hypothesis is. So जो मेरा elements of R होना चाहिए वो b0 के जगह 0 होना चाहिए, बीटा 1 के जगह 1 होना चाहिए और बीटा 2 के जगह 0 ही होना चाहिए. So that if I multiply now, beta naught multiplied by 0 plus beta 1 multiplied by 1 plus beta 2 multiplied by 0 should be equal to 0. That's why your R comes out like this. Is this clear?
Yes sir.
अब तुम इसमें अपना कोई भी हाइपोथेसिस बना सकते हो खुद। नो लेट्स से मेरा हाइपोथेसिस था बीटा 1 minus beta 2 equals 0. That is, your null hypothesis is that coefficient attached to x1 and coefficient attached to x2, they both are equal. So the elements of R, now it should be beta 1 minus of 1 होना चाहिए beta 2 के पास. Do we understand this?
Yes sir.
ठीक है? Shall I erase this?
Yes, sir.
Yeah. Guys, again I request, please don't get bogged down by the expression that we have written. बहुत ही सिंपल एक्सप्रेशन है, एक बार आप इसको अप्लाई करना सीख जाओगे तो आपको कभी दिक्कत नहीं होगा हाइपोथेसिस टेस्टिंग में, और एटलीस्ट स्टैटिस्टिक खुद फॉर्म करने में एज फार एज इकोनोमेट्रिक्स हाइपोथेसिस आर कंसर्न. ओके, ऑलराइट. सो आर बी माइनस आर which I need for this. So RB minus R will only give me B1. So just focus on this part. So this will give me B1. उसका एक scalar तो उसका transpose will be B1 only. This will also give me B1. So ये बात याद रखिएगा. अब now look at this term. ये टर्म क्या मेरा है? अब E ट्रांसपोज E अपॉन N माइनस के, इसको मैं S स्क्वायर से भी रिप्लेस कर सकता हूं, एंड सिंपली आई कैन राइट इट हियर. बात सेम ही होगा. यहां पे डिनोमिनेटर में जब मैं इसको न्यूमरेटर में लिखूंगा तो इसके इनवर्स के अंदर आ जाएगा ये. सो नाउ लुक एट दिस टर्म गाइस. ये टर्म मेरा क्या है? ये टर्म है R स्मॉल s स्क्वायर X ट्रांसपोज X इनवर्स R ट्रांसपोज का इनवर्स. नाउ लुक एट दिस पार्ट. अब ये X ट्रांसपोज X इनवर्स तो आपका डेटा मैट्रिक्स ही है, ठीक है, और उसमें मुझे पता है कि जो S स्क्वायर X ट्रांसपोज X इनवर्स क्या था आपका? वेरिएंस कोवेरिएंस ऑफ योर OLS एस्टिमेटर्स. एम आई क्लियर गाइस? प्लीज से यस और नो.
यस सर.
है ना? ये वेरिएंस कोवेरिएंस मैट्रिक्स आपका OLS एस्टिमेटर्स का है. सो जस्ट फॉर द सेक ऑफ सिंप्लिसिटी, X ट्रांसपोज X इनवर्स के सारे एलिमेंट जो ऑफ डायगोनल पे होंगे वो सारे कोवेरिएंसेस होंगे, और जो मेन डायगोनल्स पे होंगे वो सारे वेरिएंसेस होंगे. So let me write for shorthand notation so that we do not need to write this again and again. Let me write it C11, C12, C13, C21, C22, C23, C31, C32, C33. Where you should understand that all these elements which are on the main diagonal multiplied by this S square will give me the variance of B0, variance of B1, variance of B2. Guys, 0, 1 से आप कर C00, C01, C02 कर सकते हैं, because I have written B0, beta1, beta2 इसलिए. Otherwise, it does not matter. So all these elements on the main diagonal are the multiplied by this S square will be the variance of B0, B1, B2. All these elements will be the covariance term. So this will be variance of covariance of B0 with B1, covariance of B0 with B2. This will be covariance of B2, B1 with B0, B2 with B0. This again B2 with B1, and this will be variance of B2, variance of B1, and variance of B0. Is this clear?
So can you scroll up?
Yeah. और करना है scroll?
नहीं सर. सर ये S स्क्वायर कैसे आया बीच में?
डियर, ये नीचे में क्या था मेरा? E ट्रांसपोज E अपॉन N माइनस K था, डिनोमिनेटर में था. ये E ट्रांसपोज E upon N minus K is nothing but your S square, that is your unbiased estimator of sigma square.
Yes sir.
उसको मैंने न्यूमरेटर में लिख दिया इनवर्स के अंदर, कुछ नहीं किया.
Okay, ठीक है sir.
तो
Got it.
इंस्टेड ऑफ सिग्मा स्क्वायर को मैंने सिंपल एस स्क्वायर से रिप्लेस कर दिया.
Okay sir.
ठीक है.
Yes sir, got it.
ओके. ऑलराइट, सो यहां तक ये बात क्लियर है कि एस स्क्वायर मल्टीप्लाइड बाय एक्स ट्रांसपोज एक्स इनवर्स गिव्स मी वेरिएंस ऑफ बी नॉट, वेरिएंस ऑफ बी वन, वेरिएंस ऑफ बी टू, रेस्ट ऑल अदर कोवेरिएंसेस. नाउ लुक एट दिस टर्म. सो दिस होल थिंग is pre-multiplied by R first, and then the inner product of this gets post-multiplied by R transpose. So let me just pre-multiply this whole thing as, so let me write it as S square C11, C12, C13, C21, C22, C23, 31, 32, 33. This gets multiplied by R क्या है मेरा 0 1 0. So if you multiply this, if you take this multiplication, what you will get is first row, first column, first row, first column, first row, third column. So first row, first column will be C11 times 0 0, C21 times 1 C21, C31 times 0, it will be 0. So first element will be C21 plus first row, second column, C12 times 0 0, C22 times 1 C22, C32 times 0 C3 0. So it will be C22. Again, by the same analogy, only C23 term will be there. Now it gets multiplied, post multiplied by R transpose. So जब ये R transpose से multiply होगा, you see only this term will be there. That is C21 times 0 0 plus C22 times 1 C22 plus C23 times 0 will be 0. So only I'll have C22 term, obviously multiplied by S square. ये क्या है आपका? This is nothing but variance of B1, because I have used B0, B1, B2. So this C22 term is nothing but variance of B1. अब मेरा एक्सप्रेशन क्या है? इन सारे का इनवर्स. सो न्यूमरेटर में मुझे क्या मिल रहा है? Numerator में I am getting B1 multiplied by B1, so numerator I am getting B1 square, and in सारे expression का I am getting variance of B1, which is in inverse, so I'll write it in denominator variance of B1. Now if you just square root this will become B1 upon standard error of B1, which is nothing but your T ratio with degree of freedom given by n minus k. So this is your T ratio. Yeah.
Sir, please repeat that last part.
कौन सा part dear?
सर B1 स्क्वायर by
ये वाला कैसे है?
हाँ सर,
ये देखो, इसका होल एक्सप्रेशन अगर हमने क्या देखा, वहां पे वेरिएंस ऑफ B1 आया, राइट? दिस पार्ट गिव्स मी वेरिएंस ऑफ B1.
यस सर.
उसका इनवर्स आई कैन राइट दैट इन डिनोमिनेटर.
यस सर.
है ना? ये RB माइनस R से क्या आया था आपको? सिंपल B1.
यस सर. हाँ.
So B1 transpose multiplied by B1 will give me B1 square in numerator. Because ये टर्म तो सीधे नीचे आ जाएगा ना, उसको मैं वेरिएंस ऑफ B1 के लिए लिख दिया हूं यहां पे.
हाँ, गॉट इट सर.
नहीं है समझ में?
आगे सर.
एंड इसका जब आप स्क्वायर रूट करोगे, दिस विल बिकम B1 अपॉन स्टैंडर्ड एरर ऑफ B1, which is nothing but your T ratio, and this is how we conclude. We say that the T ratio of any coefficient is coefficient का value divided by standard error of that coefficient. And if this T ratio is sufficiently closer to the value 3, yesterday we had noticed that one of the property of a normally distributed random variable is कि range उसका 6 standard deviation होता है. So जितना ज़्यादा ये statistic, that is T statistic, is closer to the value 3, greater is the chance of rejection of the null hypothesis. अब इसको हम कंपेयर करेंगे किससे? जो मेरा T टेबल होगा. Am I clear here, guys? अगर नहीं, I'll repeat this point again.
Sir, they have done this proof to prove that T is equal to B1 upon standard error of B1.
Correct. And also that all these linear hypotheses can also be expressed in the F ratio form.
Okay, so.
Because you see, this T statistic, इसका square करोगे this, and this is nothing but an F ratio with 1 degree of freedom in denominator and n minus k degree of freedom in denominator.
That is F is equal to T square. मतलब that proof I've done. F equal to T square.
Is this clear, all of you? अगर नहीं, I'll repeat this point again because I'll ask you to solve the next hypothesis. Is this clear to all of you? How I have got this whole expression, how I have reduced this whole expression into B1 upon standard error of B1 only.
So,
yeah.
जो S square into variance of B आया है, B1 आया है.
हाँ जी.
So where does the S square go?
Come again, dear.
We got F ratio as not F ratio, the S square X transpose X inverse part as S square into variance of B1.
Correct.
So where does this S square go?
Because variance of B1 is S square times X transpose X ka inverse, no?
Okay, the entire term is variance.
Obviously.
Not just the C22.
No.
All right. Okay. Yes.
ये था ना?
हाँ.
है ना?
हाँ.
ये सिग्मा स्क्वायर में पता नहीं, इसलिए हम सिग्मा स्क्वायर को रिप्लेस कर दिए एस स्क्वायर से. Correct?
Yes, got it.
Okay. Now I give you a time of 20 minutes. You have to find out the expression for the hypothesis, and my null hypothesis is, again, your population regression function is, or for the this is your population regression function. Your null hypothesis is that beta 2 plus beta 3 is equal to 1. Find out the T ratio for this hypothesis. Question clear hai? Now your null hypothesis is that beta 2 plus beta 3 is equal to 1. You have to find the T statistic for this null hypothesis. Clear?
Okay.
Okay, so all right, I give you 20 minutes to solve this. I'll exactly start discussing this hypothesis as at 4:45.
सर ऊपर स्क्रॉल कर जाओ ताकि पहले वाला सॉल्यूशन देख सके.
Solution to देखना है मुस्कान.
Okay.
First, I'll request you to write the expression yourself. Expression में यहाँ पे लिख दूं?
Yeah, sure, sir.
आपका expression है RB minus R transpose R X transpose X inverse, या S square आप लिख सकते हो, या sigma square, जो भी आपको लिखना है. R transpose inverse RB minus R, और ये Q है, and this is ये मैंने एस स्क्वायर ऊपर ही लिख दिया, इसलिए यहाँ पे सिंपल लिखते हूँ, ठीक है?
Yes, sir. Thank you.
Yeah, please solve this. 4:45 I'll start discussing the question. हाँ जी.
सर एक सिली सा क्वेश्चन है।
यार सिली क्वेश्चन कुछ नहीं होता मोहित, प्लीज ऐसे मत बोलो यार।
सॉरी सर, ये क्यू जो है सर, डिग्री ऑफ फ्रीडम, वो कहाँ गया सर?
कहाँ क्यू? ये क्यू तो डिग्री ऑफ फ्रीडम इसका है ना डियर।
अच्छा, सिर्फ उसका है।
तो जो हमने यहाँ पे B0 B1 वाला टर्म जो लेके आए थे डियर, वहां पे सिर्फ एक ही वेरिएबल था ना, इसलिए जो न्यूमरेटर का डिग्री ऑफ फ्रीडम था वो वहां पे 1 हो गया था। ये क्यू जो है आपका डियर, ये डिग्री ऑफ फ्रीडम है इसका, न्यूमरेटर का, इफ यू रिमेम्बर।
हाँ सर,
है ना?
हाँ।
या
तो सर इसमें क्योंकि 3 वो है सर, तो मतलब लाइक 2 वो हो जाएगा, क्यू 2 क्यू।
आप हाँ करके देखो ना, फिर डिस्कस करते हैं।
ओके ओके सर,
ठीक है? या सो गाइस प्लीज सॉल्व, एंड 4:45 में इसको हम डिस्कस करते हैं। आई एम हियर, इफ देयर इज एनी क्वेश्चन यू कैन आस्क।